Welcome back, YouTube fans. Oh, not just YouTube fans, physics fans. Yeah, we're on our second lesson here for forces, and we're going to introduce Newton's 3 laws of motion. And you have your little sheet here to start filling in some of the notes here to help me along. I've typed some of these things up that you can copy them down. Has the nickname the Law of Inertia. An object will maintain a constant velocity until an unbalanced outside force acts upon it. Or, another way to look at it a little bit more detail, because what is a constant velocity? An object at rest will remain at rest, while an object moving at a constant velocity will continue to move in that fashion. Oh, there's my clock. You tell me what time that is. And will continue to move in that fashion until it is acted upon by an outside, unbalanced force. Okay? But now that you've memorized it, or will memorize it, let's just take a look at what it means. There's our object. It has a mass. What is its mass? Its mass is 50 kilograms. Okay? And we want to see some values of this and the speed. Right now, it's at rest. So we're not pushing on it, and it sits at rest. If I push on it, let's push with 50 newtons, it starts to move. You can see the speed up. It's speeding up. And now I tell it not to do any force. There you go. He's not doing any force. He slides along. It's not changing in speed. So the object will continue to move. It'll push more. Now it's going faster. Or maybe it'll push in the opposite direction. It'll go slower. But once that becomes 0, the object moves at a constant speed. So an object will maintain a constant velocity until an outside force acts upon it. An object at rest will remain at rest, and an object at constant velocity will continue to move in that fashion. That's Newton's first law. Here's Newton's second law. Also nicknamed the law of acceleration. The acceleration of an object experiences is directly proportional to and in the same direction as the net force acting upon it, and inversely as the proportional of the object's mass. What? Well, if you just remember, and sometimes you'll see F equals ma, and that's the simplistic way of writing it, because that's the net force is equal to the mass times the acceleration, and that's what all that means. Okay, a lot more detail in here, but there's something that we need to know. This is not just any force. This is the sum of all the forces added together. So that's going to be the net force. So sometimes I will write that instead of just F equals ma or F net equals ma, I will do this. The sum of the forces is equal to F net, which is equal to ma. Now, mathematically, this is a weird little symbol. This is sigma, capital sigma. It's a Greek letter. But that just means the sum of the forces. This means F1 plus F2 plus F3 plus, add up all the forces, F300, whatever, add up all the forces, and that's going to equal the net force. And it's that net force that causes the acceleration of that mass. And the acceleration. But not just this. This is going to be a vector. And the direction of that net force is going to be the direction that that acceleration is. The heavier object will accelerate less. The lighter object will accelerate more. So this is an interesting way of writing it. This is Newton's second law. So whenever I ask you on a quiz, what is Newton's second law? You'd go, it's the nickname, the law of acceleration, and you could just write down the formula. The sum of the forces is equal to F net, which equals ma. And hey, did you put the vector symbols over that? I love it. Okay, that would be Newton's second law. It's the formula. Let's take a look. Okay, here's a little simulator to show off our masses and forces and our speed and our acceleration. So we have a 50 kilogram object, and I'm going to turn off friction. Make it easier right now. That's when it's right down to 0, it turns icy. So it's kind of simulating frictionless, but even ice has a little bit of friction. But let's pretend no friction, none. And if I push with 50, we have an applied force of 50. The sum of the force is 50. The object's going to go faster and faster and faster. Why? Because it's accelerating at 1. Why is it going to accelerate at 1? Well, that's what we had here. The push force was 50 newtons. And the mass was 50 kilograms. So what is the acceleration? The acceleration is going to be 1, because F equals ma. Continue on. And going faster and faster and faster. Now, if I tell him to stop, boom, the acceleration is now 0. The sum of the forces is equal to 0. There actually are no forces acting on it. So the net force is 0. The acceleration is therefore 0. And the acceleration, the speed stays constant. Okay, as this is going along, let's add some friction here. Let's add 91 newtons. At 91 newtons, it's 1.82 backwards. Pause it there just so that we can hold it. 1.82 meters per second backwards, and the speed was decreasing, and I just paused it, and the speed would just happen to be 1.82 that way too. That's still moving forward. So let's just go back and take a look. Okay, just kind of understand. F net equals ma. This is still 50 kilograms. There is now no push force, but there was a frictional force. The frictional force was 91 newtons, but it was that way. It was a direction slowing it down, yet it was moving this way. Okay? So A is going to be this force, because that's the only force acting on it, no more push force. So that's the sum of the forces. So that force all over the mass. Then the net force was all the forces, which is just 91, to the left, all over the mass of 50. Pull up our calculator. (91) divided by 50. The acceleration was 1.82 meters per second squared, and it counted as negative because the direction of motion was positive. So this became a negative acceleration. The better one would have been saying positive to the left. Okay, and as we continue on, let it go down, it'll come to a stop. Once it's not moving, then the friction doesn't exist. It disappeared. Now let's push. I'll push with 50. And friction pushed back with 50. The net force was 0. Therefore, there was not accelerating. Yet I'm pushing on it. Not very movable yet. Let's push with 100. Okay. Frictional force was 100. Ooh, interesting. Wasn't it 91 beforehand? We'll explain that. I'll push with 150. There we go. I pushed with 150, it broke free, and the frictional force was 91. Let's pause it. Okay, so I'm pushing with 150, friction force pushed back with 91, the red one, friction, and I applied 150, so the sum of those two, 150 this way and 91 pushing back, 150 subtract 91 is 59. So that's the net force. And the net force of 59 divided by the mass is the acceleration, 1.18. And as it accelerates, it goes faster and faster and faster. And we'll see. And if I start pushing faster, friction is still 91. Net force is bigger. Watch what happens. Oof, when I reached 40, I couldn't run any faster. I stopped. Then friction became the net force. Now it's just slowing down. And if I play God here and take no friction, the acceleration is 0. Huge friction, 188. It stops really fast. Good. So that's Newton's second law, the law of acceleration, that we can calculate acceleration. Now, to me, in physics, this is probably one of the most important formulas of all time. At least for physics 11 and physics 12, definitely for sure, because this relates dynamics, what we're learning right now, with kinematics, the stuff we had learned till now. So this is the doorway that pulls us into the next chapter. Without that, we couldn't link up dynamics and kinematics. Let's continue on with the third law. The third law, for every action, there's an equal and opposite reaction. If object A exerts a force on object B, then object B exerts an equal and opposite force on object A. Mathematically, you could combine it this way. There's a lot of points here. I want to talk about them, but to help you out, I've typed them up. These are Newton's 3 laws. Okay, just before you copy them down, just listen to me here. Or pause it, copy them down, then listen. Okay, here it is. There are two objects. That's what we read above, that there's two objects. And when object 2 pushes on object 1, and this is going to be the applied force, then there's going to be an opposite force, the reaction force. And this will be the action. They're equal, they're opposite in direction, they're on two different objects. So they're equal in size, opposite in direction. There are two forces here acting on the two different objects. They happen at the same time. So one doesn't exist later than the other. You don't push on this and then later on the reaction force. They happen at the same time. And they are collinear. They're collinear, meaning if I draw a line, it will connect them. Let's draw the line. Boom. Okay, well, I missed it. They'll be collinear. They will have to be all on one line. These two vectors have to produce a line. In other words, if you apply a force lower down on an object, it pushes back down, lower down on the object. It just won't have one force up and one force down and cause something to rotate. It's collinear. Not that you need to really understand that. We don't even do that much in Physics 12. A little bit of rotation, a little bit about torquing. But just remember that it's collinear. And you'll often see the law of action-reaction, Newton's third law, just written down as, for every action there's an equal and opposite reaction, and just leave it like that. No, 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 no. I don't need the formula. This means that they're opposite and negative. I like these points. Okay, just 1 second. So if object A exerts a force on object B, then B exerts the equal but opposite force on object A. And these two forces are on two separate objects. Okay, so this force causes this guy to move, and this force causes this guy to move. So sometimes we'll just go F equals ma and just look on this guy. And sometimes we'll go Fm equals and just look on this guy. Or sometimes we'll look at it as what's happening with the complete system. It's like you pushing on a wall. You don't think that the wall pushes back, but it does. It does. Number one, you feel it. Number two, put yourself on a skateboard and then push on the wall. All of a sudden, you're moving away from the wall. What was the force on you that moved you away from the wall? The wall pushed on you. You pushed on the wall pushed on you. Now take two people, each standing on their own skateboard. One pushes on the other. What happens? Well, you're not tied together, so object 2 moves away, but you also move backwards, away from the way you pushed. Why? Because as you pushed on one, actually, this is the action force, you pushed on this guy, he moves away, but then you move the opposite way. And the force here was equal to the force there. That's Newton's third law. Okay, so what do you do now? Well, let's go back to the notes. Okay, you should read through this. This is all the good physics stuff. Now, as you read through it, you'll go, oh, this is what's first law. Oh, this is the second law. Oh, this is the third law. As you read through this. Okay, and then there's terminology. Fill in the blanks. There are 24 words, 24 sentences, but you might not use all of them, and you might use some of them twice. So don't just cross them out and think that it is. And fill in what you can. You might not know it all right now, so you might have to skip a couple of them and see what you can get done. Then we're going to have another lesson, and after that next lesson, we'll come back to here and you'll have more of them filled in. You'll be able to do them. So try to do as many as you can right now. Anyways, thank you very much. Subscribe, like the video. Give me your PIN number in the comments below. Oh, don't do that. Okay, anyways, chat later. Here's the dingle.